So welcome everybody to the webinar of today. The speaker of today is Christos Vassilicos, and the talk his talk is entitled Scalings of Scale-by-Scale Turbulence Energy in Non-homogeneous Turbulence. So as usual, I introduce the speaker, I introduce Christos for a minute, and then I leave him the floor. So, Christos Vassilicos is Director de Recherche CNRS at LMFL, France, and visiting professor at the Department of Mathematics and Aeronautics of Imperial College London. He earned his PhD at University of Cambridge in 1991. Between 91 and 97, he was research fellow at the Wolfson College, University of Cambridge, and from 94 to 2004 he was research fellow of the Royal Society University. From 97 to 2000 he was official fellow at St. Catherine's College, University of Cambridge, and from 2001 to 2003 he served as reader of fluid mechanics at Imperial College London. In 2003, John Christos Vassilicos became professor of fluid mechanics at the Department of Aeronautics, Imperial College London, where he remained until 2019. Since then, he is director of the Recherche CNRS at LMFL, France, and visiting professor at the Department of Mathematics and Aeronautics of Imperial College London. He was awarded the European Research Council Advanced Grant Award from 2013 to 2018. And he is principal investigator of the Marie Curie Innovative Doctor Program Multisol. He authored more than 150 international referred journal papers and supervised 34 PhD students and 14 postdocs. So it's with great pleasure that I give the floor to Christos Vassilicos. Christos, I stop sharing. If you want, you can share your screen.
Let me see. No, yes, here. Can you see the slides?
Yes, you can put it now in presentation mode, and that would be great.
Okay, I need to go all the way back just a minute. Presentation mode, perhaps this one. What is this? Just a minute. I made a mess of it, as usual. Presentation mode, perfect.
There we go. That's it. That's perfect.
Yeah, just need to find the beginning. Okay. So thank you all of you for tuning in. This is work that I did with Yang Chen, a postdoc of mine who actually left a month ago, I think by now. He now works in London. The title is Scalings of Scale-by-Scale Turbulence Energy in Non-homogeneous Turbulence. As a way of motivation, there is an observation that turbulence experts have known for a long time, and here I have a quote from Kraichnan, which goes back nearly 50 years. The -5/3 form of the energy spectrum and the equivalent 2/3 form of the second order structure function, which Kolmogorov and Obukhov predicted for equilibrium homogeneous turbulence specifically, has actually been found in many situations, many flows where the original theory does not predict that they should be there. For example, in the plot at the very bottom, which was obtained in a simulation by Alves Portela using a code array of a colleague of mine in London, George Papadakis. This is the wake of a, I assume you can see of this square here. This is a plot of the energy, and the best defined 5/3 in frequency is obtained at this position here, about 2 distances from the object. So in a region which is extremely inhomogeneous and where you should not necessarily expect it. So here are the results that were obtained in that paper by Alves Portela and Papadakis. The spectrum is a function of frequency. X1 of a D1 is here, D2 is here, 3 is here, and so forth. So at D1, you don't quite have a minus 5/3 spectrum. It's slightly shallower, perhaps minus 4/3, minus something 1.5. The best 5/3 is here at x over d equals 2, and then actually you begin to lose it a bit. And then there was a paper by Gomez Fernandez, for example, in JFM 2014. And these are just examples of such situations. There's many more. Since Kraichnan was talking about this problem 50 years ago, there will be many more, but just to give you some examples. This is the flow downstream of a grid. So grid generated turbulence. So the grid would be at this position x equals 0. And this is how the turbulence intensity would grow, because the various wakes from the grid would meet and generate more turbulence, and the turbulence then would decay after a certain distance. And this 2/3 power law here, which here is shown as divided by the prediction of Kolmogorov, so pretty nicely 2/3 divided by the so compensated by 2/3, is over more than a decade, where not far away where we are homogeneous, but actually here just before the peak of the turbulence, where actually we are pretty, the flow is still mixing, still mixing, the wakes are still mixing, we are pretty homogeneous. Those of you who may know the numbers and have read the textbooks, this constant 4.8 is actually an outlier in a way. Usually we're told it's 2, but perhaps the 4.8 here really reflects the fact that the rest of the scaling, Kolmogorov scaling, not just the out of the 2/3, but all the rest may not be absolutely right, at least in that position. So these are the kind of situations we have, and therefore we feel that there must be that Kolmogorov 41 must be a very special case of a more general theory. And in order to break beyond, in a substantial way, Kolmogorov 41, we need to go beyond these most fundamental premises. One is equilibrium, and the other one is homogeneity. So for equilibrium, work has been done over the past 10 years. I'm not going to repeat it. A new dissipation scaling has been found. The latest paper on this is by Sarkal's group, published actually this year. I will concentrate today on non-homogeneity. And I will start from a paper which was also published this year by Yang Chen and others here in Lille, who found a turbulence dissipation non-homogeneity scaling in various wakes of two side-by-side square prisms. I will explain this in a minute, and it gives us the impression that if there is such a clear scaling when you cross the flow in its most inhomogeneous direction, a clear scaling of the way the dissipation scales with Reynolds number, for example, then perhaps there's a structure to the way that the cascade in non-homogeneous flows happens, simply because the cascade is really the turbulence mechanism for dissipation. So these are the flows that Yang and Chen looked at, pairs of prisms at different separations from each other. So G over HG is the gap ratio, the gap distance between them. H is the size of them. So G over H is the gap ratio. G over H 1.25 for this, 2.4 and 3.5. And he looked inside these small fields of views in particular, which are as big as one of the prisms. And when you cross these fields of views in the cross-stream direction, and therefore you actually sample the non-homogeneity of the flow in the cross-stream direction, and actually he also showed that there is inhomogeneity in these small fields of views, then he obtained a very clear dissipation scaling, which is this one here, with a 3/2 scaling. So Ari lambda would be a Taylor macroscale Reynolds number. I'm not going to go to the details of this paper, but these are basically scatter plots now. So for scatter plots within these small fields of views, it's pretty unscattered. There seems to be some kind of law in the way that in these inhomogeneous flows, the dissipation is structured. And perhaps therefore there must be something also behind the turbulence cascade. And I remind you that this scaling law you have here is the same in all these small fields of views, in all these three flows. So basically the idea is that this kind of scaling found by Chen et al. May suggest a concept of a non-homogeneous turbulence cascade, where the energy exchanges are more complicated. And today's presentation will be an attempt at initiating research in this direction, and try to see whether we can get the 2/3 scaling or -5/3 scaling of Kolmogorov in non-homogeneous turbulence. So I'll start from a paper of Reginald Hill, or papers of Reginald Hill, where he defined, along the lines of work done already since Kolmogorov, a velocity difference. So the velocity at point x plus minus the velocity at point x minus in a flow, in a fluid, in a flow. X plus is a centroid plus a vector r, and x minus is a centroid minus the vector r. So basically we have the centroid and a separation 2r between the 2 points we're looking at, this point or that point, and we look at the velocity difference between these 2 points. There is no decomposition, it's just the actual fluctuating velocity, the instantaneous velocity. And you obtain an equation like this, where delta u is the velocity difference, ux is the sum of the 2 velocities divided by 2, so it's basically the average velocity of the 2 points. So this would be a term which characterizes how the velocity difference is advected or transported in physical space. This would be a term which characterizes how the velocity difference is transferred in the scale space, if you like, divergence of r. That's a pressure term. This pressure term, delta P, is basically the difference between the pressure at x plus and the pressure at x minus. And you have some diffusion term, diffusion in x space and diffusion in r space, the space of separations, separation vectors. So you can directly obtain an equation like this one here, which is the kind of equation we're going to use today to try to generalize a bit the theory of Kolmogorov, where again you have this transport term in physical space, a transport term in space of scales, a pressure velocity term, diffusion, and some dissipation terms, or if you want to be exact, pseudo dissipation terms. I rewrote the same equation exactly as before. So this equation here is the same as the one at the top here. I will basically now spend 4 slides to show you how, on the basis of this equation, you can retrieve the Kolmogorov theory, just for you to have an easy reference when I try a different approach in a more general setting. So, as I said, this term here is the interscale transport term. What I have done now, I have averaged over x and over realizations because I'm homogeneous. So excuse me, this equation at the top is not the same as that one. Basically, by averaging over x or over realizations in a homogeneous flow, I get rid of this term here, which is a gradient in x, and of this term here, gradient in x, and of this term here as well. So I get something simplified. That is the context within which the Kolmogorov theory of homogeneous turbulence would work. And this term here, which is a conservative in the R space, would control the exchanges between separation between different scales, energy exchanges between different scales. So it's possible to define an average turbulent energy in scales smaller than r. So I take my velocity difference squared, which is averaged over realizations or over space because I'm homogeneous. I integrate it over a sphere of size r, so the size effectively which characterizes the separation between the 2 points that define delta u. And I divide it by the volume of that sphere, so it's an average because it's averaged over the volume. That energy has 0 value at 0, you can see it easily, and tends to the 1 point kinetic energy at infinity, and you can show this monotonically increasing function of r. So if you want to think in terms of this energy now, you can apply the integral over the volume to the equation at the very top of this slide, and you obtain an equation like this one here, an equation basically of how much energy there is in scales smaller than r. And you see that you get this term here, which characterizes interscale transport, dissipation. I have forgotten an extra term which has to do with diffusion, but if the scale r you're looking at is bigger than the Taylor microscale, then you can show on the basis of very basic assumptions that the diffusion is negligible. So I write this equation as simple as this. This is the interscale transfer term, now in a situation where the flow is homogeneous. It vanishes when r equals 0, it's easy to see. It tends to 0 when r goes to infinity, so it does depend like an interscale transfer term. And at a given scale r, if this term is negative, then we have a cascade from large to small scales, and the energy increases. The energy in scales smaller than r increases. If this is positive, then we have a transfer from small to large scales, and then this energy here actually decreases, and this appears easily from this equation. If you will go further now, go back. On the basis of the equation at the top here, one more assumption made by Kolmogorov, the assumption of equilibrium, meaning that if we have a high enough Reynolds number and the scale we're looking at, so the distance or the half distance between the 2 points that we are using to sample the flow is much smaller than some integral length scale, then the d by dt term of the energy should be much smaller than dissipation. Therefore, the d by dt in this range here between the Kolmogorov scale and the integral scale is neglected, and I have basically an equation that says my interscale transfer term, the interscale transfer rate, balances dissipation. Now, if the Kolmogorov equilibrium hypothesis could be stretched all the way to scales r as close to L, and that's an assumption, extra assumption, which effectively leads to the idea that dissipation is independent of viscosity. So they are kind of related. These two statements are just made. Then you obtain this very well-known, it's called Taylor-Kolmogorov scaling, the dissipation scales like a constant independent of time and space and viscosity times the kinetic energy of the turbulence to the power 3/2 divided by the integral scale. Basically, when you go to very large scales, this term here being delta u times delta u squared will scale like k to the 3/2, and the r for very large scales, very large r's will scale like L. So this is the idea of an equilibrium cascade for homogeneous turbulence, where this rate k3 over L is the rate with which the largest turbulence eddies lose energy into the cascade, and is balanced by the way that the cascade dissipates energy at the smaller scales. So this demonstrates the central importance of dissipation as both dissipation and scale space flux, and the reason why Kolmogorov took it as a fundamental physical parameter on which to base his dimensional analysis. And here are the two similarity hypotheses that are then formulated, and which I will try somehow to replace with something else in non-homogeneous turbulence in a few minutes. I took them the way that they are written in Stephen Pope. So the first similarity hypothesis is that if we are at scales r, so the separation between the 2 points is smaller than the integral scale, then the statistics of the small scale motions have a form which depends only on viscosity and dissipation. But if we also look at scales which are large enough, so larger, for example, than the Taylor microscale, for us to be in the natural range where the viscosity should not matter, then in this range, viscosity should not matter, and all the statistics would only depend on dissipation. So dissipation is present for the reason I told you in the previous slides. And the consequence then by dimensional analysis for the second order structural function is directly this scaling that we all know, have been taught forever. Delta u squared, so something which relates to the amount of kinetic energy in fluctuations smaller than r, scales like dissipation to the power 2/3 and r to the power 2/3. This only in the intermediate inertial range of scales r. So this gives you some idea of how the Kolmogorov theory works. So now we are moving to non-homogeneous turbulence. I will go back to the equation I used above, basically this one. I'm going to write it only for one component, delta u1, in the direction of the streamwise of the flow, because I want to compare later with the data obtained by Yang Chen and Christos Cuvier in the paper I told you about. But it could have been done for other components or for the full energy. If it was for the full energy, I would have had the pressure term being a gradient term. And I'm using a Reynolds decomposition only for one of the terms, not for the rest. So only for this velocity ux, which is the sum of the two velocities. and not for delta u, which is the difference of the two velocities. I use it for the sum. So I say the sum has a mean velocity, vector velocity, and the fluctuation around it, and obtain this equation here, which says that my second order structure function is advected in physical space by this mean velocity ux. It is affected by transport, non-linear transport in physical space. By the way, as a parenthesis, perhaps also for later, if we wanted to find production terms, they are buried in here. They do not appear clearly because I have not used a decomposition for delta u. This would be the term which is a transport in scale space, so the term that has directly interscale cascade characteristics. That's a pressure velocity term, which can of course deviate energy from one component to the other and so forth, and is also very important. Two diffusion terms in the two spaces and dissipation again. So that's the equation. Again, as I wrote it before, I wrote it once more so that you can, written in words, everything in written all the words I told you before, what each one of these terms actually represents in terms of physical processes. So I'm going to try to create a framework for thinking about turbulence where we don't neglect any of these, whereas in Kolmogorov's homogeneous and equilibrium turbulence, he would neglect that, neglect this, neglect that, and only have this balancing that. So we are going to keep everything. Now, the idea is this, and that's perhaps the main idea, one of the first main ideas of this talk. We want somehow to replace Kolmogorov's two similarity hypothesis. So we make the following hypothesis, that there exists a substantial class of turbulent flows. So we haven't yet been able to document how many there are and exactly how they are characterized, but flows in which there are regions in them where these regions are of the size, for example, of a coherent structure, so not small, not big, of the size of the indigo scale. And within this region, wherever you are in this region, which is going to be a non-homogeneous region, the interscale and interspace transport processes will be similar. That's the first idea, which in the next slide I will try to formulate mathematically. Similar as long as they are rescaled in terms of the right space local velocity or space local length scales. Right, so according to where I am in space, I may have a particular turbulent kinetic energy there, a different one somewhere else, a different integral scale in different points, and I will use them to scale the different transport processes which I had in the equation, the energy equation I'm going to use, which I already showed you. So these velocity and length scales actually may differ according to whether I look at relatively large scales or small scales. So if I look at scales small enough so that viscosity may be a matter, an issue, then I should think in terms of a length scale Li, which I haven't defined yet, and which actually the theory I will develop will try to derive on the basis of the assumptions I will make. And if I try to look at scales large enough for viscosity not to matter, then it will be this outer length scale that will be of more importance. And this outer length scale will be some integral or correlational length independent of viscosity, whereas the inner scale will be a scale dependent on viscosity. And wherever I'm in space, x is the location in space, in those regions where I can make this hypothesis, for high enough Reynolds numbers, this L sub I, the inner length scale, will be much more than L sub O. L sub O will be, and I think it's reasonable to expect it to be, a local correlational length. So this similarity hypothesis, I will split it into two, an outer and an inner similarity hypothesis, and they replace Kolmogorov's two similarity hypotheses for homogeneous turbulence. And that's how they look like. Before I tell you how they look like, and I have forgotten that slide, for comparison with experimental data, I will limit myself to velocities r, which are r0, 0, and that will be important. So which we are now, of course, thinking about research in to go beyond that. So vector r will be in the streamwise direction. But we are not going only to look at structure functions in the streamwise direction, delta u1 squared. We will also look at structure functions in the transverse. So I will not speak much about it, but what I will say will apply to that one as well. And you will see later on results about that. So I will also look at delta U2. Yet U2 is the cross-stream velocity as a function of R, 0, 0, R in the streamwise direction. So here are the two similarity assumptions. The first outer similarity hypothesis is that the various terms which I have in the scale-by-scale energy budget, which I had previously, the actual structure function, the term which determines how energy is transferred from scale to scale, the term which determines how energy goes from one spatial location to another. Both of them actually come from the nonlinear term of Navier-Stokes. The term that says how velocities and pressure gradients are correlated. All these terms depend on R in a way which relates to the same function. So FO2 is O for outer, 2 for the second order structural function, FO3 outer for this third order statistic, FOX outer for this special transport, FOP outer for this pressure velocity. And the hypothesis says that wherever I am in this region of the size of a coherent structure, these quantities can always be written like this, separating the dependence on X and R in this way, where L naught depends on X, and the velocity VO2 also depends on X. Notice that my velocities VO2, VO3, VOX, and VOP are not necessarily the same. And that is something that our equations will tell us something about in a minute. So this is the outer similarity hypothesis valid for R larger than the, let's say, viscous local length scale Li. I make a similar inner similarity hypothesis now for length scales R much smaller than the outer length, which may be the integral length scale. And again, I have a similar kind of structure. The I here replaces O, so you have these functions Fi2, Fi3, Fix, Fip, I for inner now. And again, separation of variables between X and R in this way. So this is my inner similarity hypothesis. That's basically how I assume that in a non-homogeneous flow, there may be regions that behave that way. The turbulence dissipation is also, in a way, a two-point statistics because it's calculated at 2 points, at the 2 points where we sample the flow. But unlike all the other terms, it does not tend to 0 as R goes to 0. So we define C epsilon in this way. So we have the outer velocity for the second order structure function, which will be proportional to the square root of the kinetic energy at that location, and L outer, which will be the integral scale. And this relation defines C epsilon. And we assume now, and this assumption here is actually effectively akin to a similar assumption in Kolmogorov, that C epsilon doesn't depend on viscosity for high enough Reynolds numbers. So now I go to my energy balance, and I look at the outer scale by scale energy balance. So I look at this equation here, which is the equation I am using, that I used before for the homogeneous theory of Kolmogorov. I'm going to use here again in a non-homogeneous setting. I will inject my formula for dissipation, basically the definition of C epsilon, and the assumption that C epsilon does not depend on Reynolds number. And I will also inject the outer self-preservation forms into this. And obtain something like that. I do not, of course, expect you to read all this. There is no point. The main point for you to realize is that naturally, the Reynolds number appears in this form, V outer 2 LO, L outer, so this will be effectively kinetic energy square root and integral scale, appears as an inverse Reynolds number in these two effectively diffusion terms. So in the outer scale by scale energy balance, when you take R to infinity, you can neglect diffusion. That's basically what you are being told. So we have at very high Reynolds numbers, these terms here are the advection terms, and each one of these terms will be transport in space, transport in scale, transport, pressure velocity correlation term. And this is the dissipation. Now it's a matter of some simple thinking. I'm not going to bore you with it, but basically because this term here does not depend on R, you can say that each one of these terms that multiply functions of R are proportional to each other, and you find the first result that the ratio of these outer velocities, this one, and that one are all proportional to C epsilon of x. So that means what? First of all, if we were in a homogeneous situation, in a homogeneous turbulence, where C epsilon would be independent of position x, then all these velocities would be the same, in the sense that they're the same functions of x. If, however, C epsilon depends on x, very much like in the experiments of Yang Chen and Christos Cuvier that I told you about in the beginning of this seminar, then we only have really two velocities. The outer velocity for the second order structural function, and the other velocities for the transport in space in scale and pressure will be the same. So now we have reduced the problem to only two velocities if we have inhomogeneity. So now we go to the inner scale by scale energy balance, where again we inject our ansatz for the dissipation, which is actually a pretty classical one, and we inject the inner self-preservation forms into, again, this equation here. So all the physical processes are present and active. And we get something like so. Again, I don't want you necessarily to read all this. Main point is to realize that we have now our equation in terms of these inner velocities and these inner length scales. Inner velocity for the second order structural function here, inner velocity for the transport in space, for the transport in scales, and so forth. We need some kind of relation between the inner velocities and the outer velocities, the inner length scales and the outer length scales. So we write this in line with the separation of variables that we had in our inner and outer similarity assumptions. We simply say that the inner velocities squared are equal to the outer velocities times a function of Reynolds number, and this a different function for each term. So I'm not constraining too much. So G2, that would be the function for the structural function, GL for the length scale, GR for the interscale transport, and so forth, with the only constraint that these functions decrease to 0 as r goes to infinity, because of course as r goes to infinity I have smaller and smaller scales, and I assume that my length scale should be becoming smaller and smaller. So it's a normal physical assumption. I introduced this into the equation, my scale by scale equation that I had before. I don't know what this is. And I obtained this rather Kabbalistic equation here, which I'm not going to describe in much detail, but what I will want to tell you is that if you take the limit of r goes to infinity, what now disappears in the inner scale by scale energy balance is the advection term. These terms here, which basically characterize how the mean flow sweeps away the turbulent fluctuations, the structural function. And we obtain an equation of this sort here. Again, here we have the transport in space, transport in scales, pressure velocity, dissipation, a diffusion term. This is now the inner scale by scale energy balance, excuse me, the inner. So we are now looking at smaller scales. And therefore we expect
this requests that the requirement that the inner scale by scale energy balance at very high Reynolds numbers should be such that both dissipation and diffusion and one of the non-inner terms is present, gives us this relation here. Then we continue the argument by invoking an intermediate scaling for the second order structural function. We can do it also for the other terms, but not today. And therefore say that the second order structural function in this intermediate region between the inner length scale and the outer length scale is written by both the outer and the inner similarity forms, and using the relations, so the functions G2 and GL, the relations between the inner and outer velocities that I introduced before, then a simple less than a page argument gives you that this function f of I goes like a parallel of R, which already is nice, and the relation between this function G2, the function that relates the outer velocity and the inner velocity for the second order structural function, as a function of the Reynolds number, relates to the function GL, the function that relates the inner length scale to the outer, in terms of this relation here. So now we have this relation between G2 and GL, that relation which we obtained before which is there because dissipation and diffusion must be present at the inner scales, and also an exponent n. So we have three unknowns, and therefore we need something more. And this is where we introduce this hypothesis, which now replaces the equilibrium hypothesis of Kolmogorov. But it is not like Kolmogorov, an energetic balance. I'm not quite sure exactly what it is yet. I think it has to do with coherent structures, but the hypothesis is the following. It has to do with turbulence dissipation, and it says that turbulence dissipation can be obtained in the same way from both inner and outer scales. So in outer scales, dissipation is written like this, velocity outer to the power 3 over length outer. Inner scales will be like that. And we are saying that there's something in the structure of the flow that forces this particular balance. It's not necessarily in an energetic balance, I repeat. Using again these functions G that I introduced, we get now this third constraint GL equals G2 to the power 3. And now we have an answer. This function G2 goes like arg minus 1/2. This function GI goes like arg minus 3/2, and exponent n like 2/3. That is the 2/3 that Kolmogorov was obtaining in homogeneous turbulence, which we now have in non-homogeneous turbulence. Can I remove this? So we have now specific predictions that the inner length scale behaves like the integral scale to the Reynolds number of the minus 3/4. Now this Reynolds number is the square root of kinetic energy times the integral scale of the viscosity. And that this inner velocity for the second order structure function behaves like the outer velocity to the Reynolds number of the minus 1/4. Now, you might think that Li and Yi2 are the Kolmogorov length and velocities. They are not. They are the Kolmogorov length and velocities only if C epsilon is independent of x, only if we are homogeneous. Because only then epsilon and k3½ over L are effectively the same. Only then. But in general, this is not the case, and therefore, in general, Li and eta are different, even though they have the same dependence on viscosity, but they are different otherwise because of C epsilon, because of inhomogeneity. And to take the predictions a bit further, this 2/3 exponent we obtained means that this function Fi2 goes like r to the 2/3 in the intermediate range. And therefore, the second order structure function behaves like k, kinetic energy, r to L to the 2/3 times a function which is constant if we are at scales larger than the inner scale. This is not the Kolmogorov scaling, which is epsilon r 2/3. It would be the same if C epsilon was not a function of x. But given that C epsilon is a function of x, this and that are different. They have the same dependence on r, but different dependence, or the prefactor is different. So we're going to test this against the data obtained by in this paper in JFM volume 924, published a few months ago. Experiment done by Christos and Yang Chen and Yashar Ostavan. And there were two PLV systems used. First of all, there were some small fields of views with two cameras, so as to have two independent measurements of the same field, and therefore remove noise. And these small fields of views were of the size of the bars, so of the size of h by h, so about the size of a coherent structure, if you like. And in them, the resolution ranges between 4 and 2 eta, more or less. I forgot to say, this is the flow behind two bars, the flow we had before. So according to the distance between two bars, you can have qualitatively different flows. Therefore, it's a simple way to study how general this is with just one experiment and see whether the predictions are valid for different types of inhomogeneity for different types of flows. And then we also had a large field of view with a number of cameras, which was in streamwise direction about 20h or 10h according to the case. H is the size of the bar, and in the cross-stream direction about 5. This field of view was used to calculate the integral length scale. This is a 2D 2C PIV, So for the dissipation, the assumption was done that it can be calculated using the axisymmetric assumption form of it, and there are DNS and DNS now in our group by Felipe Alves Portela showing that this is actually a very good approximation. And here we calculated integral scales, both the integral scale correlation scales in the stream mass direction, both for the stream mass velocity and the cross stream velocity. For the stream mass velocity, it was a very big length scale, and very often correlation would not go to zero, so it was problematic. But for the cross stream velocity, we obtained well-defined correlations, often of the order of the size of the small field of view, sometimes it's smaller. So within the small field of view, we had all the length scales we need to look at. So these are the three different cases I told you before. Measurements in the small fields of views, of dissipation, measurements of integral scales throughout, and then used in the small fields of views by interpolating. So different cases, all these cases were looked at. And within each one of these small fields of views, the flow is quite inhomogeneous. So these are different small fields of views for the different flows. This is, the top is the flow here on top, and then this one was the next one, and so forth. Different fields of views. You see that the dissipation has different kinds of homogeneities in different fields of views, different flows. The dissipation on K3 half over L, which classically it might be, oh, what happened here? Classically, they should be equal, are actually not, because this quantity here varies like that, whereas dissipation varies like this. Quite a range of values. For example, here the dissipation goes from about 8 to 10. So within this field of views, the flow is inhomogeneous in terms of kinetic energy and dissipation, and even a little bit in terms of integral scale. So we looked at different values of y. So what am I saying here? We go inside this field of views, and I go across it in the cross-stream direction for different positions at different values of y. And this here as well was different values of y. This was actually plotted as a function of y, so I didn't say that before. So here, every one of these blue lines or red lines is for a different y, different value of y, different cross-stream position. And this would be, excuse me, this would be the second order structure function of the streamwise velocity in the streamwise direction. That is for one particular flow where we have fields of views also very close to see how things change as I go further away. So the G over H 2.4, excuse me, is actually this case here, where I have fields of views very close to the bars. And then I can see what happens as I go further away. Now, the blue is the collapse like this, in the Kolmogorov sense. The red is the collapse in the sense I was telling you before. And in fact, when you are very, very near the bar, the Kolmogorov is even slightly better, but they're both pretty bad. In fact, as we will see later on, we don't have isotropy in these flows in a fundamental way. But as we go further downstream, and this is now the last post here, and the same here, and the same will be valid for here, but excuse me, we begin to see a much better collapse in terms of the scaling I showed you in the previous slides than in terms of the Kolmogorov scalings. Now, this is the structure function for the cross-stream velocity. Again, with different values of y. Again, things don't look very well, very close to the bars. But you see here this factor 4/3, which appears, which is interesting because this is 4/3 times 0.9. We had 0.9 here. And here we have the 1 further downstream. This is 4/3 times 1. There's an interesting factor 4/3 which has been seen before, and which is characteristics of isotropy, and which I'm going to discuss in a minute. So this 4/3 multiplier relates to this relation here, which is well known, a relation between the transverse structure function and the longitudinal structure function. Now, this relation to be established requires isotropy, but also homogeneity, which we do not have here. That homogeneity implies that it doesn't mean that it's true only if homogeneity is present. So this is something we're actually studying now to see exactly why it is there. And if you introduce in that relation the formulae that were obtained by the theory presented before, you obtain that this CV defined like this, the C sub B defined by this is 4/3. This 4/3 is actually a direct imprint of the exponent 2/3. And we went to look at what this value of CV is giving us, and indeed very close, very close field is far from 4/3, actually the place where neither Kolmogorov nor the present theory was collapsing anything. But the present theory was beginning to collapse much better as soon as the CV was close to 4/3, and this is the case which is close to 4/3 for a wide range of scales, actually, of separation scales. So we limit, and before telling you the next steps, we also look at the ratio of derivatives which should be equal to 1 for isotropy, and we find that indeed, if we are pretty close to the 2 bars, it's different from 1. So the indicators, even this basic indicator of isotropy is valid once we are far away, meaning for a distance bigger than 10d from the bars, 10h from the bars. So this is now the results for the 3 flows, 1 to 25, 2.4 and 3.5, 3 flows. In the 2 furthermost stations that we have measured, they're not so far away, actually. It's a 14h from the 2 bars and 20h. They're not so far away. The blue is the collapse a la Kolmogorov, and the red is the collapse a la the present theory. I think we will agree that the present theory fares rather better. So the blue is a function of R over eta. Now, this eta is defined in terms of the dissipation scale. This is R over Ri, which is defined in terms of kinetic energy and the blue scale. And if we do the same now, not for S2U for the longitudinal structure function, but for the transverse, you obtain something similar with the factor 4/3 here. Though for the case G over H125, where you have better collapse with our formula, you have also a regime at some point which goes beyond the 2/3. And in fact, if we look at this factor CV, which should be 4/3 if we are nicely isotropic, we see that in this case of G over H125, we do get away from 4/3 for large enough scales, but otherwise we're close to 4/3. So one last attempt is to see how universally we can collapse things. So clearly, at least in this case, things collapse better in terms of the new inhomogeneous theory rather than Kolmogorov. And actually, Kolmogorov is not designed for this kind of inhomogeneous flows anyway. Here we have 2 different flows, 2 values of G over H, 2 fields of views, the one at 14 distance 14h and the one distance 20h, and 2 Reynolds numbers. And we first try to see how we can collapse them at station 14. And again, here clearly the collapse is better with the new scaling rather than Kolmogorov. How they can collapse at station 20 for different flows, and again, it's perhaps better for the new scaling rather than the Kolmogorov, and how they collapse across flows, across 2 flows, across positions in the flow, fields of views, and across 2 Reynolds numbers. So the collapse is not perfect, but it's much better than what you would have had by just manually applying Kolmogorov. And this is the same collapse for the transversal structure function. Again, same story, and I will not bother much with it. The collapse is better with the rescalings, except that there seems to be a residual dependence on G over H, which I can see, but perhaps you're not yet trained to see, but there's a residual dependence on inlet conditions. So as conclusion, I'm sorry that this took a bit longer than perhaps it should have. We developed a theory of non-homogeneous turbulence with the same number of assumptions that Kolmogorov has, but adapted to a non-homogeneous setting, which predicts that the second-order structure functions behave in this way here, where this function f sub u is actually a constant if r over li is big for high Reynolds numbers. These scalings are clearly different from Kolmogorov scalings in that they are not proportional to epsilon to the 2/3. They have the same R dependence, they have a different dependence on the actual physical parameters of the flow. They would have the same ones if epsilon was not a function of x. But since epsilon is a function of x, epsilon and this quantity here are different. And there are some new research directions, of course, that many new questions that this raises. First of all, what is the breadth of applicability of this non-homogeneous similarity and of this inner-outer equivalence? I mean, how big can fields of view be? I suspect, and we begin to also know here, work with Felipe, for example, Felipe Portela, that perhaps it shouldn't be much bigger than a coherent structure. What kind of flows does it work? I mean, we had 3 different types of wakes chosen because they're qualitatively different. I didn't explain to you exactly how they're qualitatively different, but this is documented. How can we explain the inner-outer equivalence of this dissipation that we assumed? Strong assumption, but it gave the right results. And how do we explain this non-homogeneous cross-stream dissipation scaling obtained by Yang and Chen? There is, of course, now all the other processes which are present in here. We didn't say that the flow is homogeneous. We didn't say that any of these processes is to be rubbed out, to be removed. So we have nonlinear processes present, like pressure velocity, interspace transport, and interscale transfer. How do they behave? What is the physics of relating them? Are they correlated? There's a lot of questions we can ask. What about isotropy, particularly when we talk about pressure velocity? And the picture I gave today is simply an average picture. I mean, there are fluctuations around the averages, even in Kolmogorov's homogeneous theory. The terms which are brought to zero by averaging because of homogeneity are actually extremely fluctuating, and they correlate in various ways, and the dynamics are very complicated. So here as well, we would have things like this happening. So this points at intermittency. Not only the intermittency usually thought by physicists, which is the inertial range intermittency or small-scale intermittency, but even the TNTI, the turbulent, not turbulent interface. How can we link to an equilibrium with this non-homogeneity? Because today's talk was mostly on homogeneity, not on equilibrium. The large-scale coherent structures, I believe, are very important, not yet exactly clearly how, but they seem to be important even for the non-equilibrium. How do they relate to similarity, non-homogeneity, and so forth. And we should start thinking of a different class of non-homogeneity, I believe, and so forth. So I think I will stop here and take questions. I'm sorry about the complications in giving this presentation.
So thank you, Christos, for the good. For the webinar and for such an interesting presentation. So as you said, the floor is open for questions. For whoever wants can just unmute your mic. Yeah, please go ahead.
Hi, Christos. I think maybe I missed this during the technical glitch, but can you just explain how you obtained your inner and outer similarity length scales, please?
So we assume, Ollie, that they are related by this function here, which we have not determined at all.
Yeah. I think I got this part.
We introduce this in the inner form of the interscale interspace energy balance, which is all this. Mm-hmm. When you do that, you can see by using the function g all decrease to zero as r goes to infinity. Mm-hmm. You can see that the advection term disappears, and you're left with this. Once you have this, and which is true for the small scales, you say that physically at the small scales you should have dissipation and diffusion being present. Mm-hmm. Therefore, this term here should be somewhat independent because this one is so. And so you obtain this relation between D2 and GL. GL is a function that relates Li and Lo, inner and outer length scales. G2 is a function that relates inner and outer velocities. The next step is a step that comes from the intermediate scaling, and that gives you an extra relation between these two functions and an exponent n. And the final step is this hypothesis, which I call the hypothesis of inner-outer equivalence. Where was that? This one. The fact that you can actually express dissipation both with outer and inner scales in the same, equally. Mm-hmm. These three things together give you the answers that I have here under my cursor. And therefore, this length scale, inner length scale, and inner velocity that looks like it's Kolmogorov, but it is not Kolmogorov because there is no dissipation here. There is kinetic energy and L. And it will be Kolmogorov only if you have C epsilon independent of X, because only then these two terms will be proportional to each other.
So I follow your scaling argument here, and I can see that you have the same scaling with Reynolds number as you do for a Kolmogorov scale. But how did you physically obtain your inner length scale, which you then used in the results that you presented? Because you've got a scaling argument here, but how do you therefore obtain the length scale?
In the data, okay. I calculated this Reynolds number, which is that Reynolds number I have here. L is the integral scale, is the correlation length of the cross-stream velocity, correlated in the streamwise direction. That was the correlation which actually gave sensible results which we could use. And this was from the large field of view. K was the kinetic energy. So that gave us the R, the Reynolds number, and therefore we have the inner length scale like this. Different from this, which was the dissipation scale.
So you have a scaling, but you just choose an arbitrary scaling constant, do you? 1, for example. Yes. I didn't look at the actual constant for the time being. No. Okay. So essentially, so you obtain something with an arbitrary scaling constant, and you use this to collapse your data.
Yes.
Okay. All right. Thank you very much. I've got it.
Yeah. In fact, the collapse is. Yeah. For example.
Exactly. Yeah.
And you get this nice number 1 as well.
Yeah, please go ahead with the following question. I see already Alan that's connected.
Yes. Oh, thank you. Hello, Christos. Very interesting.
Hello. Sorry, who's talking? I can't see anything.
Oh, my video's on, so I don't understand why you're not seeing
It doesn't matter.
No, okay, I'll send you a recent photo after this.
It's okay.
So we could speculate that that in inhomogeneous and even transient situations, possibly the most general form of local similarity might be in the Lagrangian frame. I wonder if you've considered that, or even think of it as a reasonable thought.
Well, the only thing I can think of is there was a paper by Vassilicos in the 50s where he generalized Taylor's theorem, you do remember, for non-homogeneous turbulence. Otherwise, I would have to see how in the Lagrangian frame I can actually isolate all the physical processes I had here. So I was able to isolate in the equation I had the diffusion and the dissipation and the other nonlinear terms. So I'm not sure how I would do it, to be honest with you, in the Lagrangian frame.
Okay, well, thanks for your thoughts.
Do you think you can do it in the Lagrangian frame?
Well, considering for general Lagrangian things like LHDIA and so on,
oh, I see.
Things get more complicated, but the point is that if you could get such an extension, you might get a broader range of observables that you could predict.
Okay, I see where you're coming from. And actually, sweeping it is a very important issue. Thankfully, in what I did today, it didn't appear so, but particularly when you look at the fluctuations around the averages, then the sweeping causes the largest fluctuations of everything. Since we talk about LHDIA. In case this gives some more information about something.
Yeah, no, yeah, well, that was basically a general thinking there, thanks.
Yeah.
Okay.
So maybe we can pass to the next question. Jim, maybe you can go ahead.
Christos.
Jim.
So yeah, thanks. This is really interesting. Really interesting. So if you go back to
sorry that your talk was terrible, but anyway. because I had to change offices and stuff like that.
Yeah, no, it was fine. It was fine. It was great, actually. So if you go back to, so I'm trying to grasp sort of what the overall key assumptions are, and I've sort of concluded that if you go back to the very beginning of your assumptions, you start with the basically separation of variables. You use that a number of places, and you start with separation of variables. You have two slides back to back where you showed separation of variables in inner scales and outer scales, and you basically said that the structure functions are given by, those, right, products of functions of position space and products of scale space. And I'm sort of, as you went through your discussion, I kind of came to the feeling that sort of the key requirement here is that the separation of variables demands that these structure functions aren't functions of sort of both physical space and scale space that are interdependent, that they can be separated in this way, which suggests that the homogeneity, the deviations from homogeneity can't be too large in some sense. That this kind of requires that if you applied your theory to progressively stronger inhomogeneities, at some point it would break down because of this this initial assumption of separation.
Thanks for this question.
And I'm wondering, am I right in thinking that way?
Yes. Well, yes. It's a very good question. Obviously, there is a lot behind this, and that could be a next talk sometime. First of all, it's not homogeneous because the terms like this transport term and this one are not zero. It is homogeneous in the sense that we're saying that wherever we are in this small region, wherever we are in this small, not very small actually, it's as big as the integral scale. Wherever we are, the processes, the nonlinear processes are more or less the same. Therefore, we cannot be dramatically inhomogeneous, but it is inhomogeneous because they are present, these processes.
Yeah. No, I get that. They're inhomogeneous. You said it. They're not dramatically inhomogeneous, which I think is why you're left with this same kind of scaling as Kolmogorov between the inner scale and the outer scale, except you make the point that the inner scale is not necessarily the Kolmogorov scale, but it scales like the Kolmogorov scale. So they scale together. Is that correct?
No, it doesn't scale like the Kolmogorov scale. No, it scales like the Kolmogorov scale in terms of they have the same viscosity dependence, but they don't depend in the same way on dissipation. Because so that's different, because that is where the inhomogeneity is actually present.
Yeah.
Another point I want to stress, because what you're saying is good, is in this term here, buried by the fact that I did not use a Reynolds decomposition for delta U, is the production term.
Yeah.
And one of the reasons actually I believe why when I was very close to my 2 bars I had problems is because the production term becomes important, but perhaps because then I cannot write this like that.
Mm-hmm.
So then get into classifying inhomogeneities. Am I inhomogeneous in the mean flow? Perhaps actually when we say not dramatically inhomogeneous, in terms of mean flow, I'm not very homogeneous, but I'm very homogeneous in terms of kinetic energy and dissipation.
Right.
Yeah, so that's where it's going.
Yeah.
If I want to include production being effectively a linear process, then I might be able to take into account such linear processes on top of this, and this is something we're working on right now.
Right. Okay. All right. Thanks.
Thank you, Jim. That helped actually that question because it helped me say something more.
So is there any more questions? So let's check the yeah, I see that Alan raised his hand, but I don't know if it's a question of before or it's just it's a follow-up question.
I forgot to lower my hand, sorry.
Oh, okay, no problem. So is there someone else who would like to ask a question? I remind you that you can just unmute your mic and ask the questions, or you can just write it in the chat box. Okay. Okay, this doesn't seem to be the case. So, well, then I think we can close the webinar. Actually, it was a very active discussion. That's always very pleasant to follow. And thank you, Christos, for the very interesting talk of today. Sorry again to the participants for the inconvenience with the internet connection. Sometimes with webinars that happens. And I hope to see you all next time. One more thing, the 2 past webinars have been recently uploaded on the YouTube channel of LMFL, and this webinar will be uploaded, I think, within the following week. So then I hope to welcome you all next week. Thank you, Christos.
Thank you, Francesco. Thank you, everybody. Bye.